Okay, so let's wait for like 5 minutes. Just тогда я веду screen sharing screen.
By the way, Yuri, I adjusted my LinkedIn script, so I'm waiting for your review on GitHub.
So now, yeah, you can come closer to the screen. Okay, it's fine. Yes, hi. So we are going to yeah, there are some like people online. So first I will do some presentation and show general flow. Yes. This is yeah. This is fine. This is fine. Like I didn't put a video right now, and this is just a screen sharing. So before we start, maybe some new people can just say something about yourself. So let's start with JDeep. So you just joined. So can you like introduce yourself? Can you hear me?
Hello everyone,
Yes. Hi.
I'm
Okay.
Jaideep. Yeah,
Yes. Hi.
I'm Jaideep
So
from
yes,
India.
are you a student or like engineer? So what are you generally doing?
No, so I'm a student at university. I'm doing my course on Bachelor of Engineering in Electronics and Communication branch,
Uh-huh. So
and I'm
where do you study?
I'm from Gujarat. That's a university, Gujarat Technological University. I'm a
Okay.
student there.
Okay. Good. So now
Yeah, thank you.
like a Pavel. So can you introduce yourself? Yes. Can you hear? Can you hear us? I think you're on mute. Yes. Anyway. Okay. So okay. So like before some like other people join, we'll go again through the whole EDA flow, and then like people are going to do some Gowin presentation. Yeah. Yes. Let me. Okay. Okay. Okay, so before like other people join, we will just do some refreshment of knowledge we did on like previous meetups, because like every time we are getting some like new people, um, like I need to just tell like a little bit what we are doing. So first of all, my name is Yuri Panchel, so let me just start a presentation. Yeah, so my name is Yuri Panchel. I work in Samsung like as a lead of one blocking GPU. So, hey, yes, and before Samsung, I was working in Juniper, and which doing block of a chip for a core router. So core routers are those like boxes which cost several $1 million, which connect cities with internet, and so now I work in Samsung, but and before this I was working in a MIPS technology, a processor company, so taking part in the development of CPU cores, which are used in like home Wi-Fi routers and in microcontrollers and in some embedded cores. And like all this time, I was using Verilog, and sometimes we were doing prototype of ASIC design using FPGA using FPGA boards, and because of all this experience, I noticed that the current education system is not perfect in preparing students for the real world. Um, like since I'm interviewing a lot of students, and I together with several other people started to create a series of practical examples to prepare students for like job interviews in electronic companies, and basically what we are doing solves several problems. So one problem is that in many schools, students are usually stuck to with one tool chain with like Xilinx, Altera, and we create examples which work on many different FPGA boards from different vendors. So not just Xilinx and Altera, but also Gowin and especially some new FPGA companies. And uh, uh, so we created it in a way that student can easily switch from FPGA board to FPGA board. So this is one thing. Second thing, because I'm interviewing students, I can see that many of them do not know how to solve microarchitectural problems with like pipeline designs. So they know how to like create a simple Verilog code with like multiplexers and stuff, and they know how to do finite state machines. But the problem is that in all those companies doing CPU, GPU, and networking, those designs are pipelined. So they need to know how to build a pipeline and how to do proper flow control. And for some reason, they are not taught this in schools. Uh, which is weird because if you look to a typical student resume, he they do advanced exercises and things like out of order CPU course and like a cache coherency messy protocols, but have like a problem with a static pipeline, and like uh, uh, yeah, next thing, we also uh, we also have exercises. Oriented for CPUs. So, and this is like pretty much it. So now this is slides from one of like previous meetings, and like a couple of links. So we have examples in a Git repository called Basics Graphics Music, which contains some like elementary introductory exercises together with more interesting exercises with graphics and with the music. So we make FPGA boards to recognize sound and produce graphics. Then we have a repository called System Verilog Homework, and by solving uh, uh, like tasks in this repository, uh, students can master their system Verilog skills from zero to the level of a job interview. Like which is important because I can see many students coming to the job interview who simply didn't master basics such as uh, 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 sequential logic, valid ready, and things like this. So they start to write something like approximate. It's like they read textbook but just didn't practice a lot. And this system Verilog homework covers this part. So now let's go back to slide. Yeah, so here is instruction how to work with examples, and most people who came to us before they went through these examples, and here is some slides, and I can share this presentation about the acronyms used in next slides. So like you, so how much you are familiar with the general flow? So should I like explain this whole flow in details or in less details? Okay, okay, yeah, this is fine. But like others, they're like kind of mixed. So some of them are advanced and some of them are not. So like I can start from like very start, like if you want, right? So basically, back in very old days, so when the very first chips were designed in like early 70s, people designed chips by simply getting like with like pencil drawing them or creating a piece of like cardboard with different color and putting them together, and then created a mask, and uh, first chips were designed in this way. And I personally actually know designer of the first microprocessor, Federico Fagin, who designed Inter 4004, and like back in year 2000, he even invested $50,000 of his own money into my startup. So we can see that people who designed the first chips, they still like around us. So then, uh, like in the 80s, electronic design automation companies appeared, which with the goal to improve engineers' productivity. And first they created tools for like automatic place and route. So you are using like you specify components and how they're connected, and they produce finally GDS2 file, which is a mask and manufacture chips. And then like in the late 80s, like in 1988, Synopsys and exemplar logic approximately at the same time invented logic synthesis from a register transfer level. So in order to use this technology, which is used for last 35 years, so like 35 years ago, many engineers were skeptical. They were saying that we manually design chips better than using like Verilog and VHDL. But then they were convinced, or Synopsys convinced people, and by the year of like 1993, a large percentage of tools were designed in this way. And this is also the time of proliferation of EDA startups, companies which quickly were adding some methodologies to this new field. So and since that time, the principles are the same, and basic principle is, so if you have some chip like a microcontroller, so you get some like system of chip which can be like microcontroller or chip in a like a Raspberry Pi or in computer, or like integrated application processor in telephone, or chip in Wi-Fi modem, or chip in like router. So you have like a system on chip which has like hardware and software part. And essentially you use system Verilog in order to synthesize hardware parts. So like eventually like transistors and like connections between them, and you have software part which is a program written in a memory. So software part is essentially a sequence of instructions in memory, and CPU is essentially a digital circuit which just gets those instructions from memory one by one and changes their internal state. So this is all what CPU is. And hardware description language is used to design both CPU and peripheral controllers. So, and here is the difference. So, in a software, when you have code, like when you have code in C, you translate this code in a series of like machine code instructions. So this is what you do in software. But in hardware, when you get this code, you translate this code first into a graph of logic elements, and then you do place and route, and this code eventually becomes like transistors and connection between transistors. So like are you familiar with this flow, and did you do like any exercises with researching? No. Okay. So basically, but do you know how to program? Basically, yeah. So like Leo is a researcher who is researching business side of startups. Yeah. So she joined us to today. So basically she is like going around and talk with different like startup founders and like large companies, and to create some paper about business practices of how like startups start, how they are funded by VCs, the process of startup product evaluation, the process of acquisition, and so on. Yeah. So basically, the principle, like, and if you can look to the history of this whole industry during 1970s, companies were mostly doing their own tools. Like I have a friend Rick who was working with me in MIPS, and he is now working in Apple. And Rick, he was working, his first job back in 1978 was in Amdahl, which was a company which created clone of IBM mainframes, right? And so Amdahl was sort of startup of its time. So like IBM was a giant company which sets a standard for mainframes, which are still used in like banks, like IBM's 360, 370, 390, and IBM Z mainframes. They're still in business, those like mainframes. But like Amdahl was a startup creating better IBM competitors than IBM itself. And Rick was sitting there in like alphanumerical display where components in a chip were pictured with like stars and minuses and pluses. So and you use the cursor and connecting those components together. And this is the way how you like enter schematics. And some of those components are gates, and other components are like D flip flops, and so on and so on. Now, so here in this like simplified schematics, green is a register which consists of two D flip flops. Yeah, and this plus is just a combination of cloud for an adder. Yeah, so like basically what was at the end of 70s is that they were like doing some rudimentary schematic entry tools, and even before that there were tools to draw like transistors and wires to create a mask on a silicon chip. Okay, now but and like their technology was at that moment not ASICs, but their technology was a combination of like elementary components like a small chip where you have like just 4 NAND gates or couple of D flip flops, or there were custom chips like microprocessors, but also there were so-called PALs. PAL is a device where you can change its logic in a device like in a so-called programmer. You can still buy programmer for like $100 in some like electronic store, and put their chip and change logic inside chip just by burning connections there. So you have some like pre-made elements, and you create connections. So this like Amdahl mainframe was created using those PALs. And then companies in like late 70s, early 80s, started to form a new industry, which is electronic design automation industry. And some startups appear. So one person I know from that era is Beer van Klimpert, who is the guy who created a startup in place and route called Silicon Valley Design or something. So no, Silicon Valley Research. Yeah. So that startup did this place and route. So you get code, you make from this code a graph with like elements like this, and then you need to place automatically this on your chip in like optimal way and create connection between them. So for this you need to create a software written by a program by people with some like mathematical thinking. So they need to know algorithms on graphs. And this is how electronic design automation industry formed. And first, there were three big companies: Daisy System, Valid Logic, and Mentor Graphics. And together they were called as a DMV, so Daisy System, Valid Logic, Mentor Graphics. And this is a sort of like word pun, because DMV is also Department of Motor Vehicle, which is the place where you get driver's license in California. Now, those companies were selling not just software, they were selling engineering workstation. So expensive computer, which cost like $100,000 with software on it. And there were like Unix-based Motorola 68,000 computers, similar to like Apple Macintosh, but larger, expensive, more powerful. And they were selling such computers to engineering organizations with a software that with a cost of like tens of $1,000 and later on $100,000 per seat. And they were selling this to large companies. And then from like a year of 1980s, they started to do design automation conference. But then people then like by the 1990s, they decided to switch to computers of other people, to computers of Sun Microsystem and Hewlett Packard. And by mid 90s, 60% of users of EDA software were using it on Sun computers and 40% on HP of computers. And at that moment, it became not like hardware software workstation business, but software business. This is how like EDA companies started. So and then many of them were essentially different part of this picture. So in this picture, you write a code, and what this code does. This code has a module which has like input ports like clock and reset, and which has output ports, just two wires, which give you number. And then you say that always when clock goes from 0 to 1, when you do like up and down, then if signal reset has like high voltage, so 0 is low voltage, 1 is a high voltage. And this voltage like back in 70s, it was like 5 volt, then it became like 3 and 3 volt, and now it's less than 1 volt. Because when you like lower voltage, you reduce power, because power is proportional to the square of voltage and to the frequency. So now and like reset, yeah, reset is not shown on there. This is like simplified diagram. You see the real diagram because this is just a slides, but they will do actual demo. Yeah. Now when you get so basically before in like early 80s, engineers were using mouse and drawing this thing with a mouse. This was called schematic entry, but this was very labor intensive. So when people switched to writing code, they gained order of magnitude engineers productivity. And then they started to look another order of magnitude, but they were not really able to find it. So this like all like high level synthesis is what I'm talking about like next level. So now what but then they found bunch of problems. So first like problem was that when they started to write a lot of code, this uh, they were getting a lot of bugs, because this is one thing when you write like 20 lines of code, and another thing when you have like 2 billion lines of code. Like now, like I'm working, so like in Samsung and like many other companies, we have amount of Verilog code which measures in millions of lines. When you have that much code, and especially because this is uh, more parallel and counterintuitive than software engineering, then you need a way how to verify it, that it really works, and how to verify it according to specification. So many startups appear in 90s in the era of verification, and one of them is a Vericity file, like startup which created language E in order to help to verify that this design behaves just like you like intended. And then there were startups, including like Chronologic by John Sanguinetti and others, which were improving simulation, because when you get this code, you and before you make chip out of this code, you need to simulate it. In order to do this, you need to use simulator, and I will show you how a simulator works. And so like after invention of basic principle of translating this code into chips, there were startups in area of simulation, verification, like additional tool to verify of correctness, then and then like in physical designs, because when those designs started to shrink, they found that they need new tools to place component on the die, because if you use old tools, it's difficult to estimate delay between components. Because when technology was like 1 micron, usually it's enough to know delay within one element. But when this goes into deep submicron, like 0.1, this all becomes called delays, mostly like interconnection delays. And you need to get people who know well physics, and who both know physics and programming and such algorithms. And this is what like EDA companies are. And Synopsys, Cadence, and Mentor Graphics, new three leaders of EDA industry, started to buy such startups in the area of physical design in like 90s. So this is basically main idea. Now this is like a pyramid of electronic industry. So we have like 2 trillion electronic industry, and we have like 500 billion semiconductor, and from this we have fabless industry and foundry materials, and finally semiconductor IP, and and the EDA licensing. But I think now numbers are different. I think now EDA size is like 8 billion or something. Huh? It's 2% of semiconductor. Okay, so yeah, so like if semiconductor is like from 4 to 5 billion, EDA is more like 8 to like 8 to 10 billion now. Yeah, this is like absolute number. Yeah. So so and the EDA company, if you go back to like 90s, the approximately half was those three large companies, and then there were many startups and small companies, but now it's more like 75% like. Huh? 70%, yeah. 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 So now it's a clear consolidation. So basically, there are very few niches for really new EDA companies, but such niches do exist because some problems are not solved. Like high-level synthesis problem was never solved. Then now, because we cannot shrink chips anymore, and because of initial cost of manufacturing is so high, uh, maybe there will be some breakthrough in microarchitectures to put many things uh, like together in multi-level die, or now Synopsys like actually hired my uh, acquaintance Igor Markov, um, who also worked in Google and Facebook to apply artificial intelligence to Synopsys things. And so far, Synopsys was using AI to just marginally improve quality of place and route, but now they want to use AI um, for microarchitecture development. So now maybe there will be some new breakthrough in that area. But this is a very mature uh, like industry right now, electronic design uh, automation, and like its mostly golden era was in like late 80s, early 90s. So now it's a mature industry, but industry which is a semiconductor IP, which is related to it, it's somewhat different because now you can see a lot of proliferation of RISC-V CPU companies, and before uh, companies doing GPU IP, and now companies are doing IP for neural networks accelerators. So yeah, now if you go next, yeah, so also one important area of EDA is now open source EDA, because tools for synthesis from Synopsys and Cadence, they all cost millions of dollars subscription fees to large engineering teams. In services like Europractice, you can get cheap licenses for university researchers, but new alternative which appear in the last 5 years is open lane, like open source tools, and uh, uh, so open source EDA tools were in business for a long time. So but they were too much unpractical. So you just write a little bit of code and it breaks. So now it is possible to use open source tools, and maybe there will be some breakthrough in this open source tools, just like Linux was in like early stage in uh, like early 90s, but then became one important platform by the end of by the end of 20th century, and now Linux is a like main server platform, and maybe open source EDA tools will also go the same way. So there are many enthusiasts, and there is a whole community of people. Hi. So there is a whole community of people working on open source tools, and maybe within like 5 years we will see something similar to what happened in embedded software. Like if you go back in the 80s or like early 90s, you can see that there were many small companies doing compilers, debuggers, and so on for various chips like C compilers and so on. But uh, uh, later on, open source solution, which is GCC. So later on, open source solution, which is GCC, outcompete those companies. And by late 90s, everybody switched from niche compilers for specialized chips into GCC-based solutions. So like and I saw how like it was going on. So both like first Motorola's 68K, then Hitachi, MIPS, AMD 29K, all those architectures were started to use like all people who program embedded chips, they started to use software derived from open source. So now maybe in the next like decade, this open source software also improves and will compete with Synopsys and Cadence, at least for microcontroller level designs. Because you cannot really compete with Synopsys and Cadence when you do like 3 nanometer design, like what we do like in Samsung, because like it's just too much stuff in it. So you need to know algorithms and all the delicate physics, and you need to have close connection with companies like TSMC and Samsung, and you also uh, uh, you also need to know customer cases, so to work with all electronic top 20 electronic companies on their like private designs, and like open source community simply cannot do this because they don't have such experience. But now some people are drifting into open source, and Google started to support open source, so maybe this will be like next area which substitutes this like EDA startup movement in like 80s and 90s. So this is possible. If you look to like China, because like Huawei is facing sanctions, they started to invest into doing alternative tool chains. So basically, if you go like in history, like there was a large campus of Huawei here in Silicon Valley on like a Thomas Expressway. And actually, I was going there inside because they had deal with the MIPS. So and what and uh, uh, but then they were like sanctioned. So recently, 2 years ago, I saw article in the Times saying that they are hiring like a lot of software engineers in China to develop alternative tool chain. But for many of companies who are doing like microcontrollers, not like high-end chips, it will be sufficient just to have a beef up open source tool chain. So, so basically, I will show you a demo of this open source, but uh, basically now this open source supports generally libraries for 130 nanometers, which are used for microcontrollers, like a microcontroller in like Internet of Things, but you cannot use this tool chain for like a chip in a telephone because it does not have enough both capacity, sophistication, ability to hold advanced timing and features. Like there are no features for like dynamic power estimation. And for instance, there is a formal tool by like a formal verification tool. One second. Just a moment. I just need to check. Wait, is it? Yeah. Okay. Unfortunately, they're not the same. They're not the same because you have different physics when you go to deep nanometer. 1 second. Oh. Yes, unfortunately, algorithm is not the same. For example, when you design a circuit and you have things which happen multiple clock cycles, you need to measure to do static timing analysis how long it takes for a logic to propagate delay within one clock cycle. Now, no, they're not, because place and route algorithm needs to be optimized by timing. So basically, they need to know that if they place two things at this distance, they need to know whether it's placed this way or this way. And in order to optimize placement, they need to know how long does it take for a signal to travel from place A to place B. And now, if you shrink geometry, you are not only getting you start to get different like physical effects. Like you cannot put two wires nearby because they will have a parasitic uh, huh? Yeah. So those physical effects. So those physical effects, they all they all change like timing, and basically in like late 90s. So in like early 90s, they were uh, assuming that there is that like delays between components are insignificant, and then delays are important only inside like end gate or something. But in late 90s, they found that this doesn't work anymore, and they went into so-called back annotation, where they synthesize, then measure parasitic effects, then synthesize again using this information. Then they do place and route, and they then resynthesize again using information from place and route. So from a waterfall model, they went into iterative model. And this whole thing became very complicated. So now open source tools do not have this level of sophistication now, which certainly limits its use, but it creates many opportunities for people who want to create open source based solutions. And there are some startups creating open source solution, and one such startup is called what is its name? It's open source formal verification tools. Uh, so um, this startup is called Symbiosis. So if you go to Symbiosis, so they're using Yosis front end, which is open source. So this is startup in like Switzerland, and they're using Yosis front end, and they uh, so they're using it with a formal tool. But the problem is that they don't support system Verilog. So, and because of it, they don't support some system Verilog assertion language created in Synopsys and other companies in late 90s, early 2000. Huh? They support system Verilog by using a proprietary front end from Verific. No, Yosis support synthesizable subset of system Verilog, but I'm talking about formal verification constructs, and they created a hack by using proprietary front end from Verific, but you cannot use such thing uh, uh, for free because Verific front end is licensed with license fee of like for startups. They were licensed it like 15 years ago for like 20, 30K evaluation license, but for big companies, we're talking about hundreds of $1,000s for a front end. I don't know where their pricing matters. This is just my guess, but they definitely have license fee and royalty. So and the Symbiosis has a version where they put together Verific and their open source stuff, but I don't know how they handle it. By the way, you can drive to like Alameda and ask the founder. So, so he's like very interesting guy from Netherlands. I mean, like, founder of Verific, of like proprietary part of it. But the person who are founders of Yosis part of it in the Symbiosis, they're in Switzerland. So this is a kind of modern day hybrid startup which uses both open source and the proprietary tool to create a solution. Maybe, but the question is whether it supports synthesizable subset or whether it supports extensions for verification. Okay, so yeah. Now, but actually, let me show them, and then we have another topic about like Gowin. So now yeah. So this is like open source editor, which is in open road, and it uses so-called magic format, which is a format for such a geometrical feature. So first you have codes, then you create graph, and then you create such transistors and wires. And the tool which allowed to like edit those like transistors and wires was created in Berkeley by the same group which created Tickle programming language, and it's still used in like open source tools. So this is how you go from code to like internal graph to this representation. This is their open source flow where you go through many steps. And the same thing is in commercial tools, but in like open source tools, it's you need to use programs created by like many different people. And now Google has a program where they allow to researchers to uh, uh, submit their designs, and if they like the design, they combine it with the CPU core and pay for the manufacturing. So you can get your chip for free. Yes, no, Google doesn't own this. Uh, Google cooperates with company called Skywater. Skywater is the only US uh, like only purely US based foundry. And they mostly were working with like militaries, doing designs with like 130 nanometers. But they made a cooperation with Google, and they like offered program called eFabless. And eFabless, so if you go to site of eFabless, if you go to site of eFabless, this is open source chip design. So they essentially allow let's do like Google eFabless. So they have a program. Yeah, make your own, yeah, open shuttle program. They have a program called open shuttle program. So what this program does is that you you get those free tools, and then eFabless and Google give you Caravelle IP, which is a template. You put your logic inside, and then there is a project submission requirements, and then they can manufacture your own chip for free if they like it. So, but if they don't like it, you can still do it for some small amount of money, like $10,000. And I actually, this is a good question. I don't know exact answer. Maybe. Yes, they have to. I don't know. You can research. Actually, I do want to know like answer to this question. What is for it in what is in it for Google? Yeah. So now like you would say that, oh, come on, this is like obsolete technology, but this is not true, because uh, uh, first of all, microcontrollers, like microcontroller which controls like engine in a car, they usually do not use technologies like 3 nanometer, because it will not survive near hot car. So if you plus it's much smaller initial cost for manufacturing. So in order to manufacture even in a commercial setting, like uh, 130 nanometer chip, you need like hundreds of $1,000s. If you need to manufacture like 28 nanometer chip, which is good enough for like even like inexpensive old phones. So like a decade ago, it was a standard in the phones. Uh, so it's just $1 million upfront expense in commercial, and just like $40,000 if you use shutters service. But for like high-end 3 nanometer chip, we are talking about like tens of $1 million. And to justify such cost, you need to have large volume. And with a smaller volume, if chip for 130 nanometer works, this is just fine. And by the way, this is why Skywater uh, was working with the militaries, because for militaries, when they do like embedded microcontrollers, this is more than enough, and they make like a radiation hardened something. which is just fine. But now we are going to more interesting question of question of FPGA. So now uh, so now let's talk about FPGAs. So FPGA is another invention of 1980s. They were invented by Xilinx in 1985, and then Altera, like for a long time, basically Xilinx and Altera were two big companies in FPGA, like sharing market, uh, like half and half plus several small companies. And then Xilinx recently was acquired by AMD and Altera by Intel, and then Intel put it separate again. But now there are many small companies coming to this FPGA market, including like Chinese Gowin, including ePhoenix. And uh, there are like many other micro semi, uh, which was before Actel. Yeah, so there are some many small. Mm, yeah. So now uh, mm, yeah, there is even like Russian FPGA company located in the city of Voronezh, which created Altera clones. But their FPGAs are very expensive, so they used only for special application. Huh? Mm, okay, okay. Yeah. Yeah. There are now companies doing embedded FPGA, like there is a French company and like several other, but this is like separate topic. So now, what is FPGA? Instead of so basically I brought like tons of FPGA boards, and I will just show them. Can you show what it is? So So here is a FPGA board, and then basically on this FPGA board, this large chip is FPGA. Everything around it's just like peripherals. This is not like new board, but this board is convenient to do demos. I have many other boards, and so uh, what what the thing is. Uh, what the thing is that this thing allows to do this thing allows to do designs without manufacturing them on a foundry. So instead of like paying like millions of dollars and then getting your chip after like several uh, months and then finding that you have a bug and you need to pay another millions of dollars and wait for another months, you can just uh, put your design to this chip, and then if it doesn't work, fix the bug and put it again within minutes. So now how like does it work? So basically it works, but it has a high cost. So basically it has element that's inside which is called loot or lookup table, which acts as a universal element. So you can change its logic function by changing configuration memory associated with this FPGA. So basically, you can just set up in memory some like zeros and ones connected to multiplexer, and now suddenly this element behaves as like AND element and another element as OR element, another like as a 1 bit of memory storage. And you can essentially put any circuit inside this chip, including CPU. But now the question is, why don't we have FPGAs in all our like telephones if they're so convenient? The problem is that in order to do this, you need to spend order of magnitudes more transistors than you would spend with a fixed ASIC technology. Because with a fixed ASIC technology, you put design to a foundry and like manufacture it there. And but with this one, like in order to have equivalent of what we have in telephone, you need to have the whole big box filled with FPGA, and such big box exists. For example, Verilog later, but it costs $6 million. Or like Intel is using Zibu, which is another emulator stuffed with such FPGAs, but in order to simulate chip like Intel chip you have in a computer, like in order to run it, you need to have like big box with FPGAs, and it will also run very slow. So like a chip in like end device cost which runs on frequency of like let's say like 1.5 gigahertz. With such FPGA box, it will run with frequency of like 10 megahertz. So like it will run 2 order of magnitude slower. Yeah. Mhm. Yes, yes. It's a purely for functional verification. Yeah. So companies which are saying emulators, they either use FPGA, like Zibo uses Xilinx high-end ultra-scale FPGAs, or for like Mentor Graphics Veloci, they use FPGA like ASIC, which is a chip which behaves sort of like FPGA, but this is a custom version of FPGA specifically for doing emulation. Yeah. And now, but this is still so like emulator is a halfway between like uh, using simulation and manufacturing. So with a simulation, when you simulator, you in order to simulate like loading, booting Linux, you need to spend several days on a simulator to just simulate this like Verilog. And in order to boot Linux on a simulated CPU, with like manufacturing device, it takes seconds, but with emulator, it takes couple of hours. So you need first to synthesize your design for the emulator, like compile it for the emulator, and then it run with uh, like hundreds of times slower. So like instead of like 2 gigahertz, it will run like 10 megahertz. But this is still much faster than with the simulation, because with the because with the simulation, it runs. We are talking about a kilohertz. So that's why that all those companies like so like every large electronic company, Intel, Samsung, Apple, like even medium-sized companies like Imagination Technology, British company, they have several emulators, and there are ideas about renting emulator time for startups. So basically, like another thing, so basically FPGAs, they have the following use. They can be used for emulators. This is number one. They can be used to teach students, and this is what we are doing. And they can be used for special applications where their limitations in frequency, power, and size are not that important. For example, like airspace companies, they created a system on their like rockets that go to space by creating network of FPGAs and microcontrollers, and then they use it to process input output and connect like many devices, connect to like sensors and to like actuators which like move things around, because they cannot manufacture custom ASIC for it, because for ASIC you need to spend like millions of dollars, and if you have like rocket with like thousands of such components, you cannot create 1,000 custom chips. So you use FPGA for a glue logic. So this is like one thing. And second, if you have very parallel design, like to process like sound from like video, from a picture, from like sonar, like sound, video, like DSP, which is digital signal processing. In FPGA, you can compensate for its problem with clock frequency with a high level of parallelism, because with a microcontroller you have a program which simply goes instruction by instruction, but with FPGA you just do many processing in parallel, and as a result you can substitute like frequency with a parallelism. So those like three main things. So special applications where it fits, education, emulation. Yeah, so this is what FPGA. So basically this is like all slides, because the rest of it I will show you. Yeah, now like basic concept of hardware description language. So this is a counter circuit kind of example, which shows the basic idea of digital logic completely. So you do something within clock cycle, and then at the end of clock cycle, you write it into storage elements, which is a D flip-flop. And uh, so we have such a simple exercise, and then we have integration
Yeah.
with like components like microphones. Yeah, so this is exercise which shows drawing on a graphic display, and some beginners exercise and music. Yeah, and the school risk processor. Yeah, so those are slides. Yeah, this is kind of prototyping boards which are in addition to emulator. So instead of using emulator, you can buy such boards which cost not like several $1 million, but like 30K or 100K, and put your ASIC design in such a high-end FPGA board. But the problem with such boards, they have limited ability to look inside what is going on. With emulator, you have a very debuggable design, so you can see every signal. And this is like a beauty of emulator. Yeah, this is one of our like FPGA boards we are using, and uh, there are such breadboardable boards where you can use them instead of like discrete components, and those are Altera boards. This is another Altera boards, and recently there is a Gowin, which is a Chinese company, which initially were using EDA tools US, like Simplify, a synthesis tool, which was created by a startup called Simplicity in like early 90s and acquired by Synopsys. So they were using that tool, but then they created their own tool, which is called Gowin ID. And in fact, after I talk and show some demo, like another person will describe how this works for Gowin. Yeah, those are Gowin boards we have, and there is another producer called Lattice. Oh, this is licensable. This is a French company called Menta. This is a startup, by the way, so you can also contact them. This is a great example of a European-based startup. So, so what they do is they don't sell hardware; they sell design. So they sell design in Verilog, which allow you to instantiate flexible FPGA cells inside fixed ASIC. So you have like a high powerful but fixed ASIC around, and you have FPGA cells inside, and you can easily reconfigure those FPGA cells. And they sell it as a soft AP to large electronic companies who want to have such a combination. And there are several startups like this on the market right now. But now the problem with such startups that it's difficult to find a good application for it. So they are trying to find a good application by like allowing to add instruction in a small CPU core, or by or one of kind of idea is that suppose a chip designer does not trust foundry and thinks that foundry can reverse engineer, like engineer something. So they put fixed design in ASIC, and then they put flexible design in FPGA cells. This is kind of another idea. Now, yeah, so now he is some like seminars. I was doing some literature. Yes, anyway, so now what I want to do is that I want to very quickly show you some demo with Altera, and then show, and then like Alexander Ryabov, we actually talk about Gowin FPGA. So just a second, let's stop that screen share, and let me, yeah, and let me make a quick demo, and after this Alexander Ryabov will do it. So now let me get, terminal. Share the screen. No, let's actually get not a terminal. Let me make a demo with a component. So I will show how this microphone is integrated with this board. So this is a microphone. You see, so we will get some sounds. You make sound, and this thing we recognize sound. Or we can start with some like simple demo. So now let's get so basics of what actually hardware engineer does at workplace. So let's get a regular like text editor called Visual VS Code. So and now let's open folder which is the basics graphics music. Save all. Let's just save whatever was here. Just temporarily save it here. Okay, okay. Let me just share this screen. Okay, so let me close this thing. Let me close everything. Okay, so let's get some like design. So let's get some design which is like not like boring, but more interesting. So let's make design which recognizes like sound. Okay, so here we are going to this design 11 node recognition. So here we have a sorry. So we are going labs. And we are going to 11 node recognition. So first, so what is this node recognition design? So here we have a code written in a language called System Verilog, and so System Verilog is a development of Verilog, and Verilog is a language which appeared in mid 80s and then developed through 90s, and there were many startups around it. At the same time, there was a VHDL language. So System Verilog is now the heaviest used together with the Verilog, which is more simple version. So here you have code which shows you that you have module, which is a block of hardware, and which has inputs and outputs as clocks and as like a reset and connections with different pins which come out from FPGA, and those connections, they have just like numbers, but we assign to this connection symbolic values because we know which pins are going to be connected with what outside of peripheral things. So here we have some pins connected to this microphone. So we will get sound from this microphone, and we will output it on LEDs and 7-segment indicators. So now inside this thing we defined wires, which are signals, and then we use constructs like always when a clock signal goes from 0 to 1, do certain actions. So what we do in this language, we define the behavior of a circuit between two edges of a clock signal. So we tell that what happened each clock. So using like old values, we create a new value. So we had like old values and we create a new values. So now like we are saying that we are getting current microphone level, and then we start counting. And when so basic idea of this thing is, let me draw it in some graphical program. Let's get like this, like easy paint. So let me switch to this. Let's start share. So basic idea is that you can let's make it. So you see clock signal goes up and down, like up and down. Okay, and the con FPG, it goes up and down with a frequency of 50 megahertz, so 50 million times a second. So basically our sound wave we are getting from a microphone is a sinusoidal wave. And we know frequency of this wave for different notes, for like A, B, C, and so on. So basically we are getting this like very frequent clock signal, and we are getting current microphone level from like 0 to like 255 or to some like level. So then this actually signed number from minus something to something. So now we are checking on a positive clock edge of clock whether before it was like negative and it became positive. So at this moment, this is the point where we start to count. And then we create a counter. So we create a counter and we count number of clock cycles. So we count, and finally it goes here. And we have in this counter we have some numbers how many clock cycles we counted. Now, if you have these numbers, because we know this frequency of 50 megahertz, we can figure out the frequency of sound. And then we are using lookup table to just see that this is the frequency, so it means this is node A or node B. You see? So now what we do is that we run the if you want to first simulate how this design work, we can actually run a script called simulate. So usually like professors do this with GUI, but in industry we are doing everything with the scripts, and like script can this is actually probably not a simulated thing. My scientific for port data. Yeah, this is the Git. Yes, there is some bug in the script. But anyway, let's synthesize it. So first we need to tell the synthesis script what FPGA board we are using. So we have a script called synthesize for another FPGA board, and our board is board number 23. Okay. So now we are going to synthesize for this board. So now we simply run this we simply run a program which converts our code into a configuration file for FPGA. This memory which determine which cells do which functions. So now like it will run for some time, and then we will see how it recognizes music. Actually, in order to recognize music, I use flute, and actually I brought flute for such experiments. So 1 second. It just got stuck. Ah, close this thing. Oh, I did bad mistake. I shouldn't start this graphic editor. For some reason, this computer can, let me move to stop share alt S. Ah, good. The changes. No, I don't want to save change. Okay, let's see. Did it finish here? Ah, yeah, I think it did. Oh, okay. Let me. Okay, now we need to connect. Now we need to connect the USB blaster. Okay, so it did synthesis. So now we need to run configure FPGA board 04. 1 second. I think I put it maybe a wrong connection. Ah. Perfect. Okay. Woo, woo. Okay, 1 second. Woo. Okay, it doesn't want to work. 1 second. Yeah, I think I need to troubleshoot what happened here with microphone because it doesn't show it. But anyway, we will do this later. So now I want to show you how the schematic looks like. Yeah, this will like troubleshoot later on. So now we can run a script called run GUI for FPGA synthesis. So now this is EDA tool called the Altera Quartus. So it is called in this version Intel FPGA Quartus. So what you do here? So let me share this screen. So this is tool called Quartus Prime, and you can see. So this is GUI. Usually, professional people rarely use GUI. Mostly use command line scripts. But this is convenient to show to like students. So you can see here different modules of this design. So like on the top is a board specific top module which connects to like outside peripherals to like buttons like LEDs, 7-segment indicators. Then it specify modules, and then you can press here and synthesize. So doing GUI, what we do in scripts. So this is like very like typical EDA tools. So you know how like they look like. So now it's doing analysis of this code. So yeah, and now like it's doing fitter, place and route, and then it is doing assembler. So now when it does analysis, you go to RTL viewer. So first you look that you had the code, right? So this is how code looks like. So this code describes what happened with circuit from clock cycles to clock cycles. So then let me share a different window. So then a logic synthesis program is running first step, which is called design elaboration, which is called compilation and elaboration. Yeah, and this create a graph of logic elements that look like this. See, so you can see logic elements inferred from this code. Then, like, you can click on this top and see a specific logic which is necessary to recognize our sound. Okay. So now, like this is the first step. So the second step is that, yeah. So the second step is that we can see technology map viewer. So, and technology map viewer is a little bit different. So visually it looks very similar, but the difference is, so here you also have like a graph of such logic elements, but those are graphs not like abstract like graph like and or bit and so on, but they are actually cells. So those are cells specific for a given family of FPGA. Like this is Altera Cyclone 4, so it shows cells specifically for Altera Cyclone 4. And now after this, you can like it does you can go to chip planner, and this chip planner shows you different FPGA cells configured on this board because this specific FPGA. Yeah, so now if you go to this chip planner, so you can also zoom through it. 1 second. Need to remove selection, need to do zoom. This thing doesn't like this window. Okay. So stop. Yeah. Okay. Let's click here. So it allocated this cells for this design in this section of the chip, and then like you can see schematic in this little window. Huh? Yeah, they're not used. They're not used. So they're just like this FPGA we're using just a small fraction of this FPGA. Yeah, but this dark design is connected to the input output pins. Yeah, black is I think input output or something. I'm not actually sure because I never looked to this level of design. So like I'm just looking to the logical level, which is common for both ASIC and FPGA. So this black is some like IO specific block, which is like an unmovable block in this FPGA. This I don't know. Yeah, this is the question to EDA tool vendor, which decided to put it here in the middle and not like, let's say here. Maybe here they have like good connection with like clocks and power and so on. Yeah, so this is how this thing look like. Now let me show you how a report look like. So when you So then you can upload it to FPGA board, but it's more complicated here than with a script. So you need to do this. Let's do hardware setup, and then we do start, and it will upload it to FPGA board. But the thing that I didn't connect here, microphone well, or maybe I disconnected, so I need to put microphone for tour. But generally, like this is how it looks like in GUI. Now in this GUI, it also gives you. So let me put it in shared screen with the GUI. So now you can see a report here. So you can view a report. And in this report, you can see that the total logic elements is 465, 148 are registered, so storage element, a number of virtual pins. Yeah, okay. And then we have static timing analysis report. So like it shows that this is a maximum clock frequency we can achieve with this design, which is 96 megahertz, but we have actually 50 megahertz. Yeah, so yeah. So now the last part of this demo is that that it produces reports, and it produces like reports about FPGA utilization. So like it does like summary, and it shows how many cells are used. So it uses 465 and 148 registers. So this register is 1 bit of memory, which is D flip-flop. So some of the cells are configured as a memory and some as a logic. And this is number of external pins it uses. And then it shows a number in clock cycles of maximum clock frequency. So like in hardware, you do some action in certain number of clock cycles, but each clock cycle has a physical some lengths like period in a picosecond, and like a reciprocal value of picosecond is a maximum clock frequency. So here is a clock frequency of 96 megahertz. Yeah, so this is like basically what we are doing with FPGA boards, so like basically in this like activity, which is doing education examples for like various universities and so on. One aspect is like elementary exercises with FPGA boards, but another aspect is more micro architectural exercises, and we will talk. So micro architecture exercises is already exercises on level of like job interview. So when you get some person in Samsung, you like ask him to build some like pipeline in Verilog, but they're using the same Verilog code, and this code expresses such schematics, but at the same time we can simulate it with a simulator, or we can synthesize it with a design. So let me show you a stereo simulator, but not with this sound. So with this sound, I don't know, maybe like I broke something with the sound, but let's show with like, let's say like uh, with school RISC-V, and I can also show how ASIC tool work. Yeah, let's go to 30 school RISC. Yeah, so here we do same thing for ASIC. So let's okay, let's say simulate 0 to, like I just want to show you a simulation example. Yeah. So you see, usually designer spends significant portion of the day debugging design in a simulator. And when you debug design in simulator, you debug waveforms. So you put the signal in time. So let me share this picture. So this is the most simple waveform viewer you can possibly have, which is GTK view. So this just shows how like processor works inside. So you are getting like clock signal which goes like up and down with a certain frequency. So you're getting reset. This is a program counter thing which shows which instruction is now executed, and then you look at like after going from reset, processor look to the address in memory 0 and extracted from there the following instruction, and then start to like execute it, and finally started produce certain data in a certain register. So we can now see that it starts producing some data in such register. But the difference is that here with this education example, we have like 200 lines of Verilog, and we have this like simple viewer. But like in a large electronic company, we have like millions of signals, and we have expensive tools like Cadence Vision or Synopsys Verdi instead of this tool. So this is a simulation, and also with this simple educational processor, we have the I will not run synthesis script because here it will run for a long time, but I will start with the code, and here is the end result. We are using this open source open road tool, and we have a viewer called open road. Yeah, so we have this viewer called open road, which just visualizes end result of ASIC synthesis. So here you can actually look inside. I think it's zoom to zoom inside, and you can zoom inside, and you can see how. So red. So some of those uh, uh, connections, they are like signals, and some are power lines, and this is a visual depiction of a GDS2 file. So GDS2 file is the end result of EDA software toolchain since like 60s. So this was invented in 60s, and this is a format with graphical representation which is sent to a foundry. So when design goes to foundry, it gets a file which has some like polygons, which some rectangles, and saying that this is the area of like silicon with a little bit of phosphorus, and this is with a silicon with a little bit of boron, and here is a metal wire of copper. So like in like old time metal wires were like aluminum wires, and then they switched to copper wires, and there are many such layers, and this is all defined in a file with a GDS2 format, which is this is a viewer of such file. Yeah. Yes, everything, like floor plan, place and route, everything. So like it went through all stages, which is like uh, uh, logic synthesis, static timing analysis, applying floor plan, placement, routing, and then it goes through like a DRC check and with like various checks. This like placement and route didn't violate rules for how close wires can be with each other, and like even some manufacturing effects, like there is like antenna effect and so on. Huh? They are buggy, and that's why they're so expensive. Uh, that's why companies are paying Synopsys for support. So there are very many sources of bugs. So, but they are they are buggy, but they use multiple layers of verification to make sure that if bug does happen, they will catch it. They simulate on all the different levels, and then they produce like a cheap prototype, and they do post-silicon debug. So they put some extra registers which they can access even after they manufacture chip. Yeah. Usually, so companies are trying to make design work from one tape out, but sometimes they even plan for two revisions. Like first like revision, and then second revision goes to the customers. Uh, it takes synthesis of a block like a mine takes like several hours, but the whole thing takes like a day or two. So the whole large thing. So like it does take some time, but after you synthesize and after you run like all like design checks, you need send it to foundry to make a set of masks. This is very expensive operation. Now we are talking about millions of dollars, and then to manufacture a test chip, and after this it goes back to the company, and then the company uh, so there are many testing on a fab itself, but they have like automatic test pattern generation. And by the way, this is like topic for several specialized startups in each area. And then do post silicon debug. Yeah. It's a relatively quick comparing to fab cycle. So we can do it many times. So like like large companies, we are doing this at least every week, because every week we are doing the whole big thing, and a designer for a block can do his own design overnight just to see how his changes affected the block. We are doing just a floor plan for a block itself, and then we check how it changes like timing and whether we went over budget. Yeah, but so like simulation takes minutes to build and simulate. In worst case, like half an hour for a block on like block level. So for block level, we're talking about like after change to simulate about like half an hour time. With like larger subsystem or the whole AP, we are talking about uh, maybe like hours for like some medium test. Yeah. Yeah. I can actually show you even in this design. So this is how floor plan looks like. So like if you never see, so you can actually specify. 1 second. There is a AC config. So they like allow to define floor plan by tickle commands. So usually floor plan is like is a specialized file which is done semi-automatically. So a specialized physical designer specifies floor plan, but also use tool to make like optimal floor plan. So, but in this open source tool for via, okay, let me find script with floor plan. So this is ASIC. Yeah, so we have config tickle, which yeah, it's here. So here we specify trivial floor plan. We are just saying that we said the die area is from 0, 0, 100, 100, which is in the microns. So we are saying that just like place whatever you have in the small square from 0, 0 to like in small square 100 by 100 micron. This is like a default floor plan, but usually in like real floor plans, we need to define the where input output cells are and more complicated, and then there is a tool with a GUI tool where they actually put floor plan as a squares or even some like areas. So usually floor plan you see it in like GUI tools, but I personally didn't do like automatic floor plan there. I just see it on like other people screen when I go past the cubicle with like physical design division. Yeah. So and yeah, but here with this like elementary example, we create only like elementary floor plan. In fact, one like person who is working with us in this like initiative, he actually wants to document all the details of doing floor plan. So this is the so we have like a plan how to 1 second. Okay, so what? So we have actually. I need to find this document. Look, anyway, so we can. So here is another script which visualizes. Here is another script which visualizes ASIC for us. So synthesis results 2. Oh, this is 09. So this is another such visualization. It's called a K layout. Okay, so this is a similar thing, but just a different flavor. Yeah. So yeah, so same thing. You can like zoom inside and see how like rows of standard cells are connected with the wires. Yeah. So you can you can see here how this end result look like. Now mostly designers like me are getting like text reports, so we don't do with this GUI representation. It's done by people in physical like physical design division. So what we do is that we are reading reports So let me show you how those reports look like. So here is our log. Yeah, so here is our log of steps. So you can see that this whole like ASIC synthesis take many steps. So it starts with like running synthesis, so it checks timing on many like in many points. First it checks static timing analysis for basic synthesis, then it does initial floor planning, then it does like input output placement, then it inserts scan chains, those registers which can be used in post-silicon debug. Then it does power planning, so it inserts power grids. Then it does global placement, so it places like large blocks. And then there is a detailed placement, which like in the past it was like channel placement, but now it's a placement in a smaller area. And this is done for the efficiency of algorithms of EDA software. Then we do static timing analysis. Then we do placement resizer design. I'm not sure what it does. Detailed placement. Then clock tree synthesis. So you have this clock signal, and this clock signal needs to go to all places in your design in approximately the same time. Otherwise, design will be buggy. It will not meet proper timing. So we have this clock tree synthesis, which guarantees that your clock signal splits into like several signals, and each splits into several signals. We finally get a clock tree where signal goes to each single element of memory, which is D flip-flop, in the same time. Now, then we do global routing, then antenna repair. It's a potential manufacturing defect. And then like on each time, it's a writing result as a Verilog. So it's still maintaining this code, this result in a Verilog description. But now we are talking not about like human produced Verilog, but automatic produced Verilog. And I will show you how it looks like. And then it does like some checking and extraction of parasitic elements, and so on and so on and so on. And finally, it generates GDS2 file, which goes for manufacturing. Now, this is the whole step. So there are like 42 steps. Now you can see Verilog produce. So if you remember original Verilog, this is how our original Verilog look like here. It's like CPU. You see, this is a human readable some form. This is what a designer writes. So now when we go, to our report, and you can see Verilog produced by the tool. So you can see that it all consists of instantiations of a cell. So this is just a little bit of code which shows that here we instantiate max, which is multiplexer, which is like hardware if for a signals that we choose between this and that signal. So this maps to specific hardware primitive. So this was from a description of behavior circuit within clock cycle to a structural description of how cells are instantiated. And here you can see Sky 130. It means that ASIC library, a library of like in case of Sky 130, it's like 100 something types of cells which are compatible with the manufacturing process in a Sky Water a company which manufactures ASICs. Yeah, so manufacturer gives this library to a designer and to EDA tool vendor, which should be compatible with the library. They should be compatible with the EDA tool vendor, and together they are together they are so like you can see the results. So this happened after synthesis. And after synthesis, so you can see that it produces big but monotonous Verilog file, which consists of many such cells. You see? Hi. Yeah. So now after placement, you still have Verilog. So by the way, header of this Verilog file is the same. So you have like signal like input and output ports. You have like bunch of wires, but then you have the very same like long sequence of such elements. But now there is a placement information which is in like different file. So now it also put like top signals and empty unoccupied cells. So see, then like after routing, it produces another one, and then like finer one. And then finer, you can see cells where you have like power and ground signals. So now you have like signals which do not have logic value, but which have just like a power and the ground. So then you can have reports. This is static timing analysis report. And basically in this static timing analysis report, in this like static timing analysis report, it tells you whether your design fits in a clock cycle, whether the timing of your design. So this means that when something happens with logic, it uses values from old D flip-flops, from old memory cells from previous clock cycle. And now it needs to produce values for the next clock cycle. And in order to do this, all logic actions takes in hardware time, in picoseconds. So it knows that before you like choose this value in multiplexer, you need to spend like a 20 or 40 like picosecond. Then you need to do some another action in order to like add things. This may take like 80 picosecond in order to add a couple of small values, and all this path should be done before your clock goes from 0 to 1 again. So like clock stores results when you finish computation and everything became stable. Then it stores in D flip-flops. Then next cycle starts, it computes something, stores in D flip-flops. Next cycle starts, computes something, stores in D flip-flops. So in order to do this, you need to have all physical delays to fit into your clock cycle. And now here you can see how longest pass through the cell. This is called static timing analysis. Longest pass through the cell, which starts from clock and goes through different cells and finally ends up in a memory element, which is D flip-flop. This is what the static timing analysis report does. And this static timing analysis is measured after synthesis, after placement, after routing, and so on. So finally, we are getting this file in library exchange format. So you can see here physical rectangles, and we are getting magic file, which is another format. And standard delay format, which is another format used by EDA tools. And this is basically how EDA tool chain works for the basic RTL to GDS2 flow. Yeah. Okay. So this is like a big picture. Then there are many niche tools which work on different aspects. So now, if like Alexander Ryabov is still with us, that we can work with him, or like I can show some like FPGA boards. Yes, he is actually with us, which is good. So now basically people who are joining Kiza like online or like coming here, they work with different FPGA boards to produce examples for the students. Yeah, but anyway, so do you have like any questions to this material? Yeah. Yeah, you can ask some simple now, or we can talk later, because now like Alexander Ryabov will present about Gowin. Huh? Okay, good. Okay, so now we can like I can get some like water, and then after this we work with Alexander Ryabov on his document about Gowin. So Alexander, are you on mute? Are you with us?
Yes, I'm here.
Okay, good. So now what I want to do, so what we do is that we are working with Alexander Ryabov on examples on a Gowin FPGA board. This is a new family of FPGA. And Alexander created a document. So I will show this document. Wait, I need to get this. I need to get this document. Yeah. So basically, Alexander created a document, and we will now edit this document for Gowin and get like inputs from everybody. Yeah. Let me get 1 second. Like I will now share the screen with this document. And like for the rest of time, we will work on this, like on this document. Just a second, now you get his document and show it to everybody. Yeah, so this is the instruction how to install Gowin EDA tools and run portable system Verilog examples. And so Alexander Ryabov created here document, and they put some preface. And now we have like 40 minutes or 1 hour or maybe more, and we will edit this document to make sure that like everybody can understand and reproduce everything which is written in this document. So in this document, Alexander shows how to get the Gowin FPGA board and how to connect it to different peripherals, to like microphones and things like that. So now, Alexander, let you to share screen, and let's listen about what you can say like about Gowin FPGAs and how this is organized. And if you want, you can also share your screen for with like terminal and run the scripts with the Gowin board. or we can just discuss document itself. So like I will stop share and you can start sharing. Okay.
Okay. Can you allow sharing?
Yeah, just a second. So first read everything you write and then make suggestions about it.
I hope you can see my screen now.
Yeah, now like I can. Yeah, can you make
Great.
larger fonts because not everybody can see this font.
Larger fonts.
Yeah, this is fine. This is fine. I think this is fine.
Okay. Hello, everyone. My name is Alexander Rябov, and I'm a student of Innopolis University. Currently, I'm one of participants of working group for basic graphics examples, and I was one of contributors into Gowin support for our examples. Basically, we have a manufacturer named Cybit, which produces the serial of boards based on Gowin chips. You can see these boards here on my screen. And these boards are available on any platform like Taobao, AliExpress,
Oh,
or
1 second, 1 second. I need to get. I need to put it on loudspeaker.
oh, okay.
Yeah, just a moment, just a moment. I need to find the speaker. I can put speaker. I can put speaker in my telephone. 1 second. Yeah, this is something I totally forgot. How to do this? Okay, let's see. Okay, what if just a second. Like I just need to put it some loudspeaker here. Here we have. Okay, now can you say something now?
1, 2, 3. Can you hear me? 1, 2, 3. Sound check.
Yeah. Can you say something?
1, 2, 3. Sound check. I can make my mic more
This is very
louder.
quiet.
Is it okay now?
1 second. Let me figure something out. I think I can connect to the telephone. Unfortunately, I made a mistake and I didn't get a loudspeaker. Yes, but this laptop is not connected to Zoom. This is the problem. I have another laptop. So can somebody? Okay. So can you connect to Zoom from your laptop and let's put your speaker? Just a second. We will solve this. We'll solve this issue.
Okay, no problem.
Yeah. So you get. Yeah. Let me. Yes, Alexander, you can continue. Yeah.
Can you hear me now? Great.
Yes,
Do I need
yes, yes.
to
You
make
can.
my micro louder, or it's okay now? Okay. Let me continue. As I said, we have Sipit company which produce many boards based on Gowin chips. There are beginners board which allow you to work with breadboards, and there are more advanced boards which have Ethernet, HDMI, or either some SPI module and GTX module which allow you to work with high-speed applications. Basically, to work this all of this board, we have two options: use the Gowin IDE by the Gowin company, or we can use open source tool chain based on USVs. For all our course, we have the main repository, basic graphics music, where we can find a lot of labs, materials, and a lot of supported boards from many of factories. Okay. Basically, now I want to present some demo, I think. Basically, when you started working with this repository, you need to clone it from GitHub and run the first script, which are placed on the root directory, which named as check setup and choose FPGA board bash. Here you can choose board which you want to work. For me, it will be SciPy board named like this. And after we continue, here we can see one moment. Can you see my text very well? Uh,
Can you make it? Can you make larger?
yes, I can. I asked about it.
Yeah,
This
yeah. Just like two times larger. It's too small.
I hear you very bad, Yuri.
Okay, okay. Yeah, this is maybe little bit larger.
I hope you can see it now.
Yeah, you can see my
And
large screen. Not sure about other people, but anyway.
uh, Yuri, I hear you very bad. Okay, I think I can continue. And after running the script, we can find the script generate information for the script generate information for every our lab and find the install toolchain from Gowin. We can see this on our CLI. After we can go to the project directory like cd labs 08 and start synthesis using this script. And after short synthesis and automatic programming, which are fault in my case because I don't have FPGA right now, we can find what we will have a running example. And I have demo in my document. One moment. And we should get something like that. Here we have reset process and the shift register when I put on bottom. Basically, we have not only synthesis script, but we also can run GUI for our example, which allow us to explore our project in GUI mode. For example, we can open a schematic viewer like on Quartus Prime software, but unfortunately, it's very, very bad to see it. But I hope you can see something. Also, we have a lot of scripts which allow you to create ASIC synthesis or synthesis for FPGA or simulation. Now I want to tell you about the structure of our projects. For every board, for example, Tang Nano 20K, we have several files. The main file is the board-specific top file, which specifies wrapper for concrete board with several parameters, input and output ports like clock ports, keys, switches, LEDs, and the GPIOs. Here we have some definitions, and later we can see what every lab will be placed here and used later when you synthesize it and flash and cure board. After we have a port definition, it's a technical file which are needed to provide information for ETA, which signal you need connect to concurrent port. This file is a time constraint file, and it's basically needed for static time analysis to provide proper work of FPGA. With this TCL file, we specify the parameters of our chip for synthesis tool. And last four files needed to run Gowin EDA GUI properly after project synthesis. And I think basically it's all for fast introduction. If you have any questions, you can ask me.
So, can you can you like explain this as a flow? So, what happened uh, when a user runs a synthesis of script? So you can start from a synthesis script in an example directory, describe how it finds the right synthesis script, then go into directory steps and show there how the setup occurs, how it builds a project, and then run a command line synthesis. So basically, I want you to explain the basic idea how examples can be adapted to a new board by explaining the structure of scripts and auxiliary files put together. So script, wrappers, project file, and like what a person needs to do in order to adapt examples for a new board.
Okay,
So
but
let's start
this
from
is
line
very
zero
boring, I
six
think.
synthesizers. You can just go inside the script and show that it tries to find the main script and then show how main script looks like. So
Okay,
can you do it?
one moment.
So let's start from a script 03 synthesize for FPGA in that one in example directory. Yes, so we can see this is the file. Yeah. So we have a directory called lab, and this is as example shift register. We just show shift register on the board. I can actually demonstrate to like everybody shift register on another board. So let me quickly configure with shift register. So this is how just a moment. Yeah, so I have a, so this is Saltera board. So let me quickly synthesize and run shift register on it. I'm doing it now. So shift register is a basic exercise in the very start of digital design course with the labs. And it just shows bunch of, yeah. So you can see that it just shows a bunch of D flip-flops connected together, and those D flip-flops are connected to LEDs. So I press a button and I made a new movement of a, and we are using here enable, like a clock enable signal, which is generated from a counter. So this is kind of basic HDL example. Yeah. And so we start in this example directory. So, and we are using bash script, which is portable across Linux and Windows platform. So what does this bash script do? So since we have many examples and we don't want to copy the full like long script for each board to each place, in all those places we have just a small script which redirect to a true script. So here you can see that this bash script, first it's trying to find a real script by going up the directory tree, and then it finds in a directory called scripts steps. So now you can start from here and then show this 0C synthesis. Yeah. So we are going here. So first it runs a script called setup source, and this setup source looks what kind of EDA tools are available and put some settings here. Yeah. Okay, so you can continue describing it. Yes.
Okay.
Yeah.
Yuri, maybe I give this opportunity to you because I'm not want to present scripts.
Huh?
Yuri, can you continue presenting scripts because I cannot do this. Sorry.
Oh, you cannot show it, or you are not sure about structure of the script here.
I'm not sure about presenting this in the right manner.
Huh?
I'm not sure about presenting this structure of the script in the right way.
Yeah. So let me tell a couple of things about structure of the script. So let me share my screen. 1 second. So if you go, so if you go to GitHub directory where the repository is located, so let's start from there. So you're going to GitHub. So what happened is that small script from a small script from a directory with example finds a real synthesis script here, which is 03 synthesize for FPGA. And then first it runs a setup script, and then it So if you go to setup script, you can see that it's doing like a lot of actions. So it's uh, uh, finds it has bash script routines for like error messages and for checking what is available for checking whether it's running under Windows or Linux, and then it runs some tool specific setups, and then it checks for a current FPGA board, and if board is not defining, it is asking what FPGA board you have, and then it sets up a project directory and figures out what do you need to run with a given board. So this is such a setup. Now, if you go into Gowin specific directory, you can see that it is trying to find where Gowin directory setup is located. So it is first checking for an environment variable called Gowin version dir. And if this Gowin version dir has a sub directories ID and ID bin, then it sets path using this sub directory, so user can specify the exact location of Gowin installation by setting this environment variable. Now, if this environment variable is not set, then it is expecting going in a path, right? So go and finish setup and report where found. No, it's actually more complicated. So we start from a function called setup ID, and from a function setup ID, first we are looking whether Gowin version directory is defined, and if it's defined, we call this function Gowin finish setup. And if it's not defined, we are trying to check whether we have Gowin shell in the path. And if we have Gowin shell in the path, then we instruct a location of the Gowin ID from there. Now, if you don't have it in the path, we check another environment variable, which is called Gowin home. And by going home, we mean a parent directory where multiple installations of Gowin with different versions are located. So, and if such variable is not defined, in this case, we are trying to find installation like under Linux, either in home directory or in /opt or in /tools. And under Windows, we are trying to find it on drive C, drive T, and drive E. And once we found it, we call function finish setup and report where found, where we set up a path, and we set up environment variables for different Gowin tools we call in our like other bash scripts. So now when we know where our Gowin is located, we go back to the synthesis script, and in a synthesis script, in a Gowin, just a second. Yeah. So once we did all the setup in our synthesis script, we run another script which setups run directory, and run directory is used to store all the temporary files there. And by the way, user doesn't have to know it. So for user, this is just a one push button solution. User just runs a synthesis script and that's it. And so like this explanation is for those people who want to port it to a new FPGA board. Yeah. Yeah. So yeah, you're like absolutely totally right, and this is the reason, why we generally avoid just running something from a path, and we are trying to set up direct path in a variable. So you can see here that we said Gowin ID full real path. So we have environment variable with this real path. And then in our synthesis script, we actually call environment variable from this real path. So if you go here to synthesize, so first we are trying to simulate the synthesizable portion of this design using Icarus Verilog. So we are using Icarus Verilog as a sort of lint pre-synthesis. Then we also run assembly for processor examples. So for examples that don't use processor if you don't run. Yeah. Restore. Yeah. Yeah. So usually when you export pass and call another script, when you exit from this script, I believe it is restored automatically, right? It is not restored only if you do source. Yeah, if you do source, it is not restored. But if you don't do source, it is restored. So now we let's go back to Gowin specific setup. So in this Gowin specific setup, we have a function setup run directory. So this is a directory where we store all the temporary files. So basic idea with those examples that we don't pollute the place with source file with the temporary files. We store temporary files in a run sub directory, so that if we remove this run subdirectory, we remove everything. And in order to set it up, we create a project inside, and this like project is called this is called FPGA project tickle. And so we start with a board specific tickle, and then we add so tickle in tool command language is a language created by the same guy who created Magic, the tool we showed before. And it is used in EDA tools since like early 90s as a way to to run the tools to do some like complicated synthesis and set options. So we are adding additional lines to this project, and this is the way how we create a project. So we start from a basic project for the board, which is in a board specific, like here we have like 10 nano 20K, right? So we start from this board specific TCL file, which sets a device and sets certain synthesis options. And then we add file names we are going to synthesize to create a project in a run directory. So now maybe Alexander, you can show that project created inside run. But before this, so what else do we have here? Also, we have here a CST tool, which is a Gowin way to map FPGA pins to a symbolic names. Like all this stuff happen is not visible by user, but we need to do this to make our scripts compatible with a wide number of FPGA boards. Yeah, so now if you go back to scripts and to steps, so if you go to scripts and to steps, oh wait, we need to go to setup Gowin. So here we create a project file and finally we run synthesis. So we create project file. So finally, all we have to do when we run synthesis, we are getting Gowin executable, and we use TCL script as an argument to this executable. And this is how it synthesizes the thing. And we also have a configure script. It's a script which uploads the design in FPGA board. And this configuration can happen in either by using open FPGA loader or by using another one. So maybe Alexander can tell more about it. Yeah, so this is like basic structure of the script. So we are hiding from user all this activity in a bunch of bash scripts, and bash scripts are finding specifics for the boards and construct a project file and run synthesis. Yes, this is the way how we can deal with the many boards. Yeah. Okay, Alexander, so can you now elaborate more on Gowin tools?
No, I think maybe
Oh, wait,
open
we
source
don't hear you
toolchains,
for some reason.
but
Okay.
maybe open source toolchains, but I think it's not now. But it's very interesting theme, I think. But I want to maybe prepare some presentation for it, but not now. Can you hear me?
Yes, but can you speak louder? Can you speak louder?
Yes, I can.
Yeah, okay.
I said I think it's all for Gowin script with Gowin toolchain because there are not so many scripts and important nodes which are needed for typical script user. But if we will discuss maybe open source toolchain later, I can prepare maybe something interesting and show it, but not now, I think.
Yeah, so basically now I want to go through, like I want to go to. Next step in this Gowin activity is that like everybody need to read this document, and this document should be improved. So both like language should be improved, and everybody needs to put some questions which should be explained here better. Because we need to create a document which like anybody can use to run all examples on a Gowin family of the board. So just like we have some rough document for Altera boards, but we also want to create a similar document for Xilinx boards. Yeah, and for Efinix board. Yeah, I think yeah. Alexander, I will do pass through this document offline, and like I can share this document with the mailing list of like everybody who gave me a mail, and put this should be viewer copy link. So I will put it to the chat. So now we need to review this document and prepare the final version of this document in like maybe like 2 months time frame. Or maybe earlier. So if you can do it in
using the Gowin, using the Zoom
like
chat,
couple of weeks, this is great.
using the Zoom chat goes away. If you could put it in something like Facebook or something more permanent than the link, than the chat for the Zoom meeting.
Doesn't want me to. One second. I should use different computer for Zoom. Yeah, I should use different computer for Zoom. Just a second. Close. Sorry. Yeah. Okay, so I will just paste this file here, so you can review it. So you can review it and yeah, so you can review it and create a copy of it and add your comments. Yeah, okay. So now I think we can have some discussion about some short discussion. So we will finish it soon. So we can have some short discussion about like you wanted to talk about the Python infrastructure for this. So
right? This pretty like verbose and redundant, right? So you have all those four specific top files, which mostly like copy each other with the only difference is like this mapping of signals, right? And so you can basically you can have one template of this board specific top file, and you can move all the mapping into configuration, right? And then you can have also bash scripts, like they basically they're all again copy of each other, right? And then the only thing that bash scripts those bash scripts pass is their name basically, right?
But those small bash scripts you cannot really avoid them because if you don't put them, you need to type something. But here is those scripts, you can just press enter
That's
like
not
MC or
that's not a problem by itself. So the problem is
redirect is I think is not a problem.
yeah, the larger problem is that when you start taking peripherals to those boards, right? You need for each new combination of board and peripherals, you need to create separate board specific token file, right? And you, in theory, you can have like many different combinations. So you can attach this like one peripheral with like buttons and 7 segments, and you can attach different peripheral, and you can have multiple combinations of those peripherals, and you will need to have either you need to either handle this by like changing defines inside, right? And that's not like very user friendly. You need to like dig into it. And
Yeah, we should get rid of most of defense. Defense is kind of not a good way of.
so the idea is basically to have a script that kind of generates, so based on some template, generates this board specific top, right, for a specific board and combination of peripherals, right?
You can try, but please don't make it more labor intensive to define new devices. And also, so there are like two advantages. One advantage is that it is more labor intensive to. So if you don't want to create yet another language to define ports. This is what I can do. They like invent languages for the coders. And if you don't want to have yet another language which people need to learn in order to generate wrappers for one more board. It's like one thing. Second thing is script should not take initiative in mapping to the pins. Because if you map to the pins, like suppose you see the pins like 10, 12, 13, 14, 15, I remember, okay, let's map to those pins. Script shouldn't do this because the problem is,
Sorry, I'm late.
it's okay. I mean, we are supposed to finish soon, but we are went into a discussion mode. Yeah, so like Kirk was working in the NASA for that project is like Mars rover transmission of data in like 90s. And like interestingly enough, I actually remember that I saw him when I went to NASA like back in 1997. Yes, I totally forget, but now I remember how you like entered the door, who these people were with 86.
So, all right, so when in 1997 were you at JPL?
Yes, I was in July, just the moment there was this transmission from Mars in the cafeteria. I went there with another person to make presentation about like a C2HD translation. Then JPL assigned some students, so some like choice to like evaluate. And like I think I saw it. I might be mistaken, but then like I totally forgot, but then suddenly I remember suddenly someone had a picture in my brain. So wait a second, wasn't really given. Maybe because
Well,
I remember like the structure of this building and like if it was used just after like to move to this, but then like I went somewhere else.
I was just surprised.
Maybe it's false.
No, I during that time period, I was running around constantly between buildings and stuff, so I know it could have happened.
Huh?
It could happen. So was the main cafeteria like by the courtyard.
So like a event is a large cafeteria where there were large monitors showing translation from
Yeah.
So
Mars.
Yeah, that sounds right.
yeah, so
there
there
were
are some like rails,
it was like
metal rails, like in this.
Yeah, that,
Yeah.
there's two main cafeterias. And we piped in feeds into both of them. Because, you know, it was like the focus of everything. So it sounds
Is it like
awesome.
in Pasadena? Or?
Yeah, it's JPL in Pasadena.
Yeah, and then like I remember some like a long like a corridors with the room, and there was the one room where like we did the presentation. So like when with the latest Coleman was my investor in the thing. We were actually using a report from JPL as an argument to our first venture investors. Like, look, we went there, they actually played with our
You know, I would be surprised. I mean, the reason why I was so famous in that time period is because everyone had money in the stock market and internet stocks. I mean,
Yeah.
that was the reason why people followed it so closely, because they had money in it.
Yeah.
You know, they had money in the stock market. So, you know, that's like a once every 100-year type event. You know?
Yeah, nothing like this happened after that. Yeah, and this all started in 1995 with like IPO of Netscape.
Yeah.
And then like everybody went crazy because before this, in order to get like in order to make IPO, you have to have profitable company, and before that, like company valuation for like venture capitalists, they were doing like $3 billion valuation was considered like okay. Like and after this, I talked with a venture capitalist who says that wait a second, it's just 2 months. Like everything changed now. 3 persons with the 2 pieces of paper they call with like 2 pages they call business one company and says that they have $20 million evaluation pre-investment. It's like something totally different world. Yeah, so like everybody was like crazy, and like at that moment, so you actually is writing paper about venture investment in India at that time. That's why you're talking about it. So like basically, at that moment. This all went crazy, and nothing like this happened before, or after that time from 1995 until 2001. But what was important about like Kirk's Marx translation was that there were many people who were talking that who were saying that internet is going to collapse because number of users rises exponentially, and it is limited by the bandwidth of internet infrastructure. And at that time, internet routers were had like low bandwidth because they were based on like software processors and stuff. And like later on, like Juniper invented this processing packets in ASIC outside of CPU, and this and bandwidth of routers suddenly became like 2 orders of magnitude high. But at that moment, in 1997, in the summer of 1997, there were no such routers. So this was a big challenge to get information from Mars and actually transmit it to a bunch of internet users around. And actually, so Kirk was doing that.
Yeah, so basically the deal with that was that we first tried to go to the National Science Foundation backbone. So that's the only thing the government had available to it, right? But I did the numbers in my head. And I said, well, it's never going to be enough. And so I partnered with Sun and Silicon Graphics and SGI and CompuServe, you know, and then what we did is we limited the size of the images we put on the site to be fairly modest. You know, that was back in the days of like the modems, you know, the 56K baud modems. There was no fiber optics. It was all modems back then, you know, connected to your phone line, right? And so because I had mirror sites all over the place and the bandwidth of the website was limited, it worked, you know, but it was a hack. It was like a massive hack by today's standards, you know, but it catalyzed the growth of the internet, and then people figured out how to solve all these problems.
It's called like edge services now, right? So it's when you have a lot of mirrors that are like in different regions.
Yeah,
right.
Yeah, this is before Akamai, before all the major bandwidth providers, before all these sophisticated systems. It was none of that was in place. But anyhow.
Yeah, so you invented CDN, right?
Well, I really don't think I did. It was a hack. It was a really successful hack, you know. But interestingly enough, what brought down the internet was not Mars Pathfinder. It was Monica Lewinsky. It was Monica Lewinsky, the Star Report. That actually
On the Drudge Report.
Well, you know, Monica Lewinsky had that deal going on with Clinton, and they published that report on all the scandal, right? And they put that on the internet, and that actually almost brought down the internet. Yeah.
Like I remember also in 1995 there was this Unabomber thing, which people badly go to like but Monica Lewinsky, I didn't realize.
Yeah, Monica Lewinsky, and then also the Victoria's Secret fashion show. Also.
That's
Yeah, but Mars Pathfinder did not bring down the internet. It did not make a dent in it, but the other things did. You know, but anyhow, ancient history.
Like also I was talking with a guy who was looking live on Mars using results from those missions. He was also working with the JPL, but he's in Arizona, but I forgot his name. Yeah, this was interesting. Yeah, but like apparently like JPL was looking at various things, including using FPGA, but their intern actually didn't analyze carefully. He wrote that the tool does not process pointers except for pointers to characters, which was incorrect. So, but anyway, it looks like a JPL was doing a bunch of various research of all the kinds.
I believe that. I believe that they were trying to figure out clever ways to do things, but the commercial sector, you know, had so much more money and firepower.
Oh yeah, but this was a nice reference for the VCs.
Yeah.
Somebody.
You know, at one point we were going to try. This is really hysterical. At one point, there was a proposal to expand the internet out into deep space. That we were going to like implement TCP/IP through some hack, you know, across the deep space network, which would have been, I think, a disaster. But that's how crazy things were back then.
Oh wait, you mean by transmitting?
Yes, you know, the big antennas. You know, the three big antenna sites in Goldstone, Madrid, Spain, and Canberra, Australia. Right, we were going to like try to implement a protocol that approximated TCP/IP and expand the internet out to our spacecraft. But you know, because of the time delays, it was really stupid.
Yeah, like I know that there was also some like there was some like a protocol used in space application called SpaceWire, but I'm not sure whether it has any connection with this. So
It's conceivable. I mean, in low Earth orbit, you can do it. You can expand the internet out to low Earth orbit and even geosynchronous, but you can't expand it all the way to Mars and Jupiter.
Delay is too large.
That's exactly right.
Okay.
Yeah, that's right. That's exactly correct. There's no good reason to do it.
No, there's no good reason why.
Okay, anything. But anyway, so I think that we are done for like talking for today. So now like now we talk here about different FPGA boards, and so like Alexander, I will do pass through your document, and basically we have a set of certain specific tasks. So we need to figure out how to port to Kintex 7 board. Like I also was experimenting how to run examples under, not only under Windows and Linux, but also under Windows Linux subsystem. And plus we discuss how to create new examples for like processor exercises. So, and like those of you who are not working on a certain task already can actually contact me if you want to add your board, or if you want to add your some example. But before this, you can read my Haber article, and it is very important if you are trying to improve your qualification. It's very important to go through homework exercises, because you want to guarantee quality of new examples by making sure everybody is trained on like old examples. Yeah. So okay, so I think we are now, we go to strictly like offline discussion with the board. So you can like stick around, but I will stop like talking, and we will just record whatever we discuss internally. So thank you, everybody. Yeah. Okay. All right. So now, what is lots of different boards in different schools. So some like school have some like rare boards, and basically it's not practical if you are training like several hundred of people to buy for them on one standard board. So that it's better to put it on to put examples portable to different boards. this is actually what this activity is of activity, and another thing that because like I'm interviewing students and like in the like current job and previous jobs too, I noticed that many of them come from schools without practical skills in certain areas, and we have examples for this too, like for building static pipeline, flow control, and so on. Yeah, so like if you want to, so what is your current level of expertise in Verilog? With the microcontrollers. Okay. Yeah, you can start from scratch with those. You can start from scratch with those like examples. If you follow my like recommendations and read literature and do homework, you can go to the level of proficiency. But there are several counterintuitive things on the way. But you just need to push some efforts in several areas, and then like assuming that you're doing all of those exercises in like maybe like half a year, you will be at level better than most of graduates. So okay. Okay, so Leo, so did you get necessary basic information for research for it? Yes, sure. Okay, so like you can, yeah. So thank you, and contact me if you need like a reference to those EDA companies and so on, so on. Yeah. Okay, thank you. Bye bye. Yeah. Okay, so and what are you doing? Uh, but for a student, wait 10,000 so they get so they certain some some So what they I after exact yes. 16. So plus so so now my Yeah, for software for software for software interviews there are like many sets of interview questions, but for hardware interviews, like everything I saw are like like is a primitive question, like some like or no, not primitive question, but they're not applied to like actual. There are questions about basic sequential logic. So like if you go not to like not like the architecture side you can not to run with this the cap probability except can be but if you go to like let's say like airspace say who put a combination of controllers and FPGAs, they actually are left they solve different aspects. So like instead of making such things that yeah, so okay, so we stop recording. So thank you everybody.